Hello everyone. Welcome to the. Thanks for joining in. Just drop a message in the chat box whether the slide is visible and my audio is audible or not, and we'll begin in 2 or 3 minutes. Okay, so we are gonna wait 1 or 2 minutes more if any other participants join in, and then we'll start. Yeah, so let's begin. I am Uddipan Sarkar, core committee member at ISTE-VIT Vellore, and today I'll be conducting this webinar, dive into DSA, and I'll try to help you gain a very brief understanding on the basics of DSA, that is data structures and algorithms. So before we start, like when we code stuff, I'll be using the language CPP, that is C++, and I'll be using my compiler, that is code blocks, and not necessary that all of you need to use code blocks as well. You can use VS Code, code blocks, or any other compiler that you have. And if you don't have any installed on your system, you can just go to Google, type C++ compiler. So hello, am I audible? Just someone write in the chat box. Hello. I am audible, right? So yeah, I was just saying, if you don't have any compiler installed on your system, you can just go on to Google, type C++ compiler, and use any of the online IDEs that are there. And if you have code blocks or VS Code or anything else installed on your system, then you can just use that. So once again, welcome everyone to dive into DSA, and I'll try my very best to help you gain an understanding on what DSA actually is. So let us begin without any further ado. So this is the table of contents. This is what we are going to do today as part of this webinar. We are going to learn about what data structures and algorithms are. We are going to know what recursion is. It is basically a technique of coding. And we are going to study about two data structures, that is stacks and queues. So let us begin. So first, I'm going to introduce DSA to you. So before we try to understand what data structures and algorithms are, we must first understand what a computer program is. It is basically a collection of instructions, and they perform a very specific task for the user. And for this purpose, the computer program may need to store data, retrieve that data and perform the computations upon acting upon the instructions given from the user. Now, what is a data structure? A data structure is basically a location in our memory to which we have given a name. And this location is used to store or organize this data in different manners. And coming to what an algorithm is, it is a collection of steps, a set of computations which we use to perform the particular problem given by the user. So why do we learn data structures and algorithms? This is because it allows us to write efficient and optimized computer programs. So why do we need DSA? It allows us to process data in an easier manner and allows information to be stored very efficiently. It is necessary for designing a very efficient algorithm and provides management of databases. We can access the data in any time and anywhere in a secure manner. And there are several practical use cases of data structures, and they have been given here in the slide. You can just go through them for fast data lookup, data indexing, IP addressing, and so on. So, coming to our first topic of the day, that is recursion. Now, what is recursion? Recursion is a method in computer science where the solution to a problem depends on solutions to smaller instances of that problem. So basically, we take our problem, we divide it into smaller parts, and we use the same process on each of the smaller parts. And then we get our answers from these smaller parts, we combine them together, we perform some small calculation, and then we get our final answer. In other words, when we use recursion in our codes, our function calls upon itself to solve these smaller problems. So that is what recursion is, and it may sound a bit vague, but once we start coding, uh, I hope all doubts can be cleared. So how does recursion work? You see, the function here keeps on calling itself. Now, there must be some kind of a terminating condition at which this function will stop calling itself. This base condition is referred to as the base case. Now, this base case is very important in a recursive function because if we do not design our base case properly, our function will keep calling itself. There will be no termination and it will just keep on running endlessly. So that has to be avoided. Now, after the base case has been designed, we go for the recursive call. This recursive call is basically where the function calls upon itself. It calls itself again upon a smaller version of the problem. For example, we need to perform some kind of a calculation on our input. So when our function calls itself recursively, it just passes on a smaller part of that input and it performs the same computation on that smaller part. Now, while writing the recursive call, we need to be very careful because it is very important to figure out what our smaller problem is. A- And we need to design it in such a manner that the solution of our original problem depends on the solution of this smaller problem. And finally, we have the small calculation. In each recursive call, when we get our answer from the smaller problem, we have to do some kind of a computation on this. We just do some calculation on this and then we return it to the higher function. Now, not necessary that the order always has to be this in a recursive function. The base case always comes first, but the recursive call and the small calculation steps can be interchanged depending upon the requirement of the problem. So this is how recursion basically works. Now, we should start with our first code of the day. This is a very simple question. We just give an integer to the compiler, and our program just finds out the sum of all the digits in our number, and then it returns to us. Now, you may have done this code in a very normal manner, but this time we are going to do it using recursion. Now, I may be using C++ to solve these questions, but even if you understand the logic, you can just try to code it in whichever language you feel comfortable, whether it be Python or Java. So let us begin with our first code of the day, that is write a recursive function that returns the sum of the digits of a given integer. So let us begin. I'll just head on to code blocks. So I have designed a part of the code beforehand, that is the main function, and I have just written down the header files. We will basically be coding this function, the sum of digits function. This will calculate the sum of all the digits in our number and return us the final value. So now, as we learned in recursion, first we need to define the base case. So what is our base case going to be in this case? Now let's just imagine we have one number and we need to find the sum of all its digits. So what do? We have to first separate. We have to find out what our smaller problem is. So the method that I have thought of is that each time when I call my function recursively, I just separate the last digit out from my integer and I pass the remaining digits to the recursive call. And then my recursive function brings me the sum of these remaining digits, terminating condition. That is going to be our base case. So our base case is going to be if our number becomes 0, then we return 0 because no sum remains to be found since our number has become 0. Now once the base case has been designed, now we think of the recursive call. Now what we had decided, we are going to separate the last digit out from our integer. So first we need to find the last digit. Now to find the last digit, we use the very simple line int d is equal to our number mod 10. So this will cause our last, we'll have stored the last digit of our number in the integer d. Now that we have stored the last digit, we are going to pass the remaining digits. We call our function and we pass n by 10. Now why do we pass n by 10? This is basically to remove the last digit from our number. Each time our function recursively calls itself, it progressively removes one digit from the end of our number. Now in recursion, we have to always assume that our recursive call is going to bring us the answer for the remaining steps. Provided we have designed our base case correctly and we have written our small calculation correctly, the recursive call should always bring us the answer. So assuming that my answer variable stores the sum of the digits of all the remaining digits in the number, now all I have to do is I have to add my last integer d to this variable answer, because answer stores the sum of digits of the remaining digits in our number and d stores the last digit. So we just add these two and that is the value we return. So we return answer plus d. So once to revise, we have our base case, that is when our number becomes 0, that is our terminating condition, we return 0. Otherwise, we separate the last digit out from our integer and then we recursively find the sum of the remaining digits in our integer, and then we add these two variables, the last digit and the sum of remaining digits, and that is the value we return. Now in the main function, we have taken a number from the user and we have called our function sum of digits on that number. So now let us try to execute it. So let's take a simple input 1, 2, 3, 4, 5. So it should return us 5 plus 4, 9 plus 3, 12 plus 2, 14 plus 1, 15. And we see that it returns us 15. So this is how recursion works. Progressively, we divide our original number into smaller numbers. That is, we remove the last digit from our number and we call recursion on the smaller parts. And each time when we get our answer, we just add the last digit to it. Just excuse me for 1 second. I'll be right back. Sorry for that. There was a bit of an issue. So yeah, I am back. So yeah, this is how recursion works. We take our number, we remove the last digit, we find the sum of the remaining digits using recursion, and to our answer, we add the last digit. So now that we have done our first code, are there any doubts? Please type them in the chat box. So since there are no doubts, let's just move on to our next code. So this time we are going to work with a string. So here the question is, we have a string input and we need to check whether our input is palindrome or not using recursion. So how do we do that? First, we need to now in this also I have already pre-designed some functions, that is the length function. This is going to return the length of my string, and I have designed the main function as well, and we are going to code for the check palindrome function. So let us discuss the problem. So we have an input. Let me just go back to my slide. We have an input race car. Now, how do we check whether this is a palindrome input or not? So in a palindrome input, we have to check that the character at our first index is the same as the character at our last index or not. If they are same, we check whether the character at the second index is same as the character at the second last index or not, and so on. We go on checking from the beginning as well as from the end. Now, we have to design our terminating condition. So what is that going to be? In case of this problem, we are checking from the beginning as well as from the end. So when will we stop? We will stop when we have reached basically the middle of our string input, because once we reach the middle, we have gone through all the characters from the beginning and all the characters from the end, and we have found that they are all same. So that means that our input is palindrome. So now let us code for this. Now, as we discussed, we need to check from the beginning as well as from the end. So we will need to maintain two pointers. One pointer points to the beginning and the other points from the end. Now, to do this, our check palindrome function only has a single character array as our parameter, so we need to use a helper function, and this will have our pointers as well that will point to the beginning as well as to the end. So now we code our helper function. So we just now decided that our base case is when we have reached the middle of our string input. Now, when will we reach the middle of our string input? We will do so when we have iterated through the first part of the input and we have iterated through the last part of the input as well. Basically, when our end variable and our start variable reach together, when they meet each other, that is when we have checked through our entire string. So how do we do that? We just find out the distance between our end and our start, and then we just check whether our distance is 0 or distance is 1. These are the two cases where we will terminate them. This is because if our character input is of even length, then the final distance will be 1, after which the start and the end variables will cross each other. And if our input is odd in length, then the final distance will be 0, after which the start and end variables will cross each other. So we have to take care of both these end conditions. Now we have declared the conditions, and since we have done so, once we have reached the middle of our input, that means that we can now just return true, because we must have checked through all the other characters before reaching the middle. Now that is our base case done. And after our base case is done, we are coming to our small calculation. So here we check the character at our start index with the character at our end index. So we code for that. Now, if they are equal, that would mean that our characters are same, and so we will move ahead. We will check if the next characters are same or not. But if they are not equal, that means we know that our string is not palindrome, so we can directly return false. Now otherwise, our characters are same, so we now check the next characters. We just have have a bool variable b, and we recursively call our helper function again on our input. And now, since we are going to check the second character with the second last character and so on, we are going to increment our start variable with 1, and we are going to decrement our end variable with 1. And our bool b will store the true or false value of whether they are same or not. And after this, we are just going to return b. So this is our helper function. Now coming to the check palindrome function, we need we need to call the helper function here. So we just write return helper. Now we send our input as parameter. Our start index is 0 and our end index. Now with this, we once go through our helper function. The base case is when our end meets our start variable. That is when distance becomes 0 or distance becomes 1. That is when we return true. Relation, we check whether the character at our start is equal to the character at our end or not. If they are not equal, we return false. And if they are equal, we just move on. We compare the second character with our second last, then the third with our third last, and so on. So the code seems to be all right. So let us run it now. So our sample input one was race car, which is a palindrome word. So yes, the program returns to us true. So this shows that our code is working perfectly. Let us just use another input, something which is not palindrome. Let's give the word samurai and it returns false. So this shows that our code is working perfectly. So basically this is how recursion works. So if there are any doubts about recursion, please type them in the chat box or else we'll just move ahead. So now we move on to stacks. So this is our first data structure that we are going to study, stacks. So let's move on. What are stacks? Stacks is also a linear data structure like arrays and linked lists. It's an abstract data type and it follows the LIFO order of data insertion. This basically stands for last in, first out. So just imagine there are a pile of books on your table. Now, if you just want to add another random book on that pile, you're going to place it on top of that pile. And if you just need to reduce the length of that pile, so you just remove one book from the top of that pile. So basically the book which entered the pile last is going to be the book which leaves the pile first. That is how a stack works. The last element that we insert into our stack is the first element that comes out of the stack when we need it to. So these are the operations that we are going to have in our stack. The insertion, which is known as the push function. Deletion, this is known as pop. We also need to have access to our topmost element. This is a very basic requirement of stack. The user only has access to the topmost element in a stack. And this function and the top function is the one which performs this operation. Then we also need to know the present size of our stack. So we design a size function for that. And then we also have to check whether our stack is empty or not. And this is done by the isEmpty function. So now moving on, how do we implement stack using an array? Now in an array, normally we can access any element we want. Now I'll try my level best to explain it to you. So this is the stack I have designed. There are the header files, iostream and climits. Climits is basically required when we want to store our variable with the lowermost or the uppermost values that can be assigned to it. For example, we have our int index. Using climits, we can initialize our integer variable with the lowermost integer allowed by C++ or the uppermost integer allowed by C++. Now, coming to our stack class. So these are the private members. If nothing is mentioned about the access specifier, C++ considers them to be private to a class. So we have the integer pointer data, we have an integer variable index, and we have an integer variable capacity. Now coming to the public functions. We have our constructor. It is a parameterized constructor which has one integer as a parameter, and then we initialize our data array with this value that has been passed through the constructor. We write data is equal to new int s, so we have now created an array of length s. We initialize our index with -1, which basically denotes that our stack is empty as of now, and we initialize our capacity with s. Our capacity is the maximum size that our stack can have. Now we come to the size of stack function. Here we directly return index plus 1. This is because uh, C++ follows zero indexing. So our index is always going to be 1 less than the actual length of the stack. So we directly return index plus 1. Coming to the isEmpty function, we check whether our index is -1 or not. This is because we had initialized index with -1. So index is only going to be -1 when our stack is empty. So if our index is -1, we return true, else we return false. Coming to the push function, through which we are going to pass elements into the stack. We have one parameter, that is the element we are going to pass into the stack. Now the very first thing that we need to do is we need to check whether our stack is full or not. Now when is our stack going to be full? The condition has been given here if index is equal to capacity -1. The same reason C++ follows zero indexing, so the uppermost index is always going to be 1 less than the capacity. So we check whether we have reached our last index or not. If we have done so, this means that our stack is full, so we print the message stack full and then we return without doing anything. Otherwise, now we know that our index points to the topmost element. So if we want to insert another element on top of this, we first increment our index. We increase it by 1, so it points to a new location in the array, the next location, and in this location we insert our element. So this basically means that our element has been added to the stack. It is now on top of the previous element. And now we have pushed our element into the stack, so that's it for our push function. Now coming to the pop function. In the pop function, the return type has been specified as integer. So not only will this function remove the topmost element from the stack, it is also going to return it to the user. So like in case of push function, we checked whether our stack was full or not. In case of pop function, we check whether our stack is empty or not. Now, how do we check that? This basically means I am returning the lowermost integer that C++ allows, and this I am doing to denote that my stack is empty. So I print the message stack is empty and I return. Now if my stack is not empty, I have to return the topmost element, and then I have to reduce my index so that my index points to the second last element now, because once our topmost elements gets removed, the second last elements becomes our new topmost element. So I write return data of index minus minus. Now note that I have used the post increment operator here, which basically means we will return the data of index value, and then our index is going to decrease by -1, basically pointing to the new topmost value of our stack. And by doing this, we have lost all access to the previous topmost element, which basically means that we have removed that element from our stack. So that's it for the pop function. Next, we have the top function. Our top function provides us with the topmost element, and it does nothing else, unlike pop where we also remove the topmost element. So it is going to be nearly similar to the pop function. We first check whether our stack is empty or not. If it is empty, we print the message stack is empty and then we return int main. Otherwise, we return the data of index. We do not change the value of index here since the top function only and only returns the topmost value. It does nothing to that value. So that's it for our stack class. Let's just revise. We have our constructor which takes in the size of our stack as the parameter. We have the size of stack function which returns the size of our stack. We have the isEmpty function which tells us whether our stack is empty or not. We have the push function which inserts element into the stack, and we have the pop function which removes elements from the stack, and the final top function which gives us the topmost element. Now to test whether our stack is working or not, I have just given a sample code here. First, we declare stack s of 5, which basically means that the maximum size our stack can have is 5, or it can hold at most 5 elements. Note that I have designed the stack for integer. However, if we use templates, we can also design the stack for characters or double or any other data type. So in this case, I have been using integers. So declaring stack s of 5 means that our stack can at most hold 5 integer values. So after that, I have pushed in 1, 2, 3, 4, 5. Now these 5 elements are going to go in to the stack. Now when we try to push in 6, uh, our stack is already full. So as we had coded, it should give us the message that our stack is full. And then we print s of top, which would give the topmost element. Now since the last element we had inserted is 5, so our topmost element now is 5, so this should print 5. Now then we call the pop function 5 times. 1, 2, 3, 4, 5. So on calling the pop function 5 times, the first time it's going to remove 5 from the stack. The last element was 5, so 5 is going to be removed from the stack, and it's also going to print 5. Now after 5 has been removed, 4 is the topmost element, so it prints 4 and then removes it, and then it prints 3 and removes it. It prints 2 and then it prints 1. After the fifth pop function, our stack has become fully empty. So now when we call the size of stack function, this should return to us 0. And then we call the isEmpty function. Now since our stack has become empty, so this should return true. Now if it returns true, that basically translates to 1 in C++. So this is what our output should look like. Stack full. When we try to push in 6, then s.top gives us 5. Then the 5 pop functions give us 5, 4, 3, 2, 1. The size of stack gives us 0, and the isEmpty function gives us true, which means it gives us 1. So now let's try to run it. And here we compare it with our. It's going to be a very tedious task to create a stack each time we require it in our program. So to bypass this difficulty, C++ provides an inbuilt stack in its standard template library, and this can be used instead of creating or writing a stack class each time we need it. To use this, we have to just use the header file #include stack, and the syntax to declare a stack, declare the inbuilt stack of C++ is this stack. We specify the data type and then we give the variable name. For example, if you want to create a stack of type integer with the name st, we write stack int st. This basically means we have created a stack which can hold values of integer. Another advantage of the inbuilt stack in C++ is that it has no upper limit. You can keep on pushing as many values as you want in this stack. Unlike the stack that we designed where we had a limit, the inbuilt stack in C++ does not have any limit. So the respective functions are push, pop, size, empty, and top. Note here that in the stack that we had designed, we had given the return type to the pop function as int. So it would also return the value after removing it. But in case of the inbuilt stack, the return type is void, so it will only remove the element from the stack. It is not going to return to us the element. If we want to access the topmost element, we have to use the top function. And the size and empty functions are basically self-explanatory. So now that we have studied what stacks are, so let us solve one code in our using our stacks. So the question is, we have a string expression and this contains only round brackets, and we have to check whether our expression is balanced or not. The brackets are said to be balanced if the bracket which opens last closes first. Basically, it means that all the opening and the closing brackets should be balanced. If there is a single extra opening or an extra closing bracket, this means that our expression is not balanced and the output will be false. Otherwise, the output is going to be true. Now, one example of a balanced expression has been given here. Here, all the opening brackets have their corresponding closing brackets, and we have to code in such a manner so that we get our desired output. Now, how do we do this? Let us first think about this question, and let us think how we are going to use stacks to implement this question. So we have to check whether for each of our opening brackets we have a closing bracket or not. So how do we do that? The method is actually very simple. First, we iterate through our entire expression, and whenever we find an opening bracket, we just directly push it into our stack. So after we have iterated through the entire expression, all our opening brackets have been pushed into the stack. After this, we again iterate over the expression, and this time we check for the closing brackets. And each time we get a closing bracket, we must check whether the bracket is balanced or not. Now, how will we know that the bracket is not balanced? We will come to know that our bracket is not balanced if there is no corresponding opening bracket to it. So when we get a closing bracket, we are going to check whether our stack is empty or not, because that is how we come to know that it is not balanced. If our stack is empty, it means that the closing bracket has not been balanced, which means that our expression is unbalanced. And if our if our stack is not empty, that means there is an opening bracket. So we just pop the opening bracket out of our stack. Each time we get a closing bracket, we just pop the corresponding opening bracket out from our stack. Now, this goes on for the entire expression. After we have gone through the entire expression for a second time uh, to match the closing brackets, we check whether finally our stack is empty or not. If our stack is empty, this would mean that all the closing brackets have been nullified by the opening brackets, and so our expression is balanced. If our stack is not empty, that would mean that there are some opening brackets left. So this means that the expression is not balanced, so we return false. So now let's move on to the implementation. So now we need to code. So like we discussed first, we have called the header file stack, so we can use the inbuilt stack in our function. And since our expression is of type string, so our stack should contain only character values. So we write stack character variable name. Let's name it S1. So now we have named it S1. Now we discussed we need to iterate over the entire stack. So we write for I is equal to 0, expression I not equal to null literal. Now in C++, that is basically in any language, whenever we give a string input, What the compiler does is that to the end of the string input, it always adds a null literal, which is this. This is used to denote the end of a string. So when we need to iterate over the entire string and we don't know the length, we can just check whether we have reached the null literal or not. If we have reached the null literal, it would mean that we have completely gone through the entire string. So now we have given the for loop conditions. So now we check whether our present character is an opening bracket or not. If it is, we push it into our stack. And this basically goes on in the entire loop. We push all the opening brackets into our stack. Now after this, we have to now check for the closing brackets. So we once again iterate over the entire loop. Now this time we check whether our present character is a closing bracket or not. Now once we have done that, there are two conditions that we need to take care of. One is that this closing bracket is balanced or not. Now, if this closing bracket is balanced, there is going to be a corresponding opening bracket in the stack. If it is not balanced, then our stack will have become empty by now. So we first check if our stack is empty or not. We can use both the size function or the empty function for this. I am going to use the size function. So if s1 dot size is 0, we return false because our bracket is not balanced. Otherwise, we remove the topmost element from our stack. Now this goes on for the entire loop, and at the end we check whether our stack has become empty or not. If our stack has become empty, the function will return true, and that means that our expression is balanced. If our stack has not become empty, it means there are some unbalanced opening brackets, so we should return false. So we can directly write return s1 dot empty. So this should give us the output as we have predicted. So let's once go through it. We declare a stack. We insert all the opening brackets into the stack. Then we again go through the expression and we check for the closing brackets. And if our closing bracket is not balanced, we return false. Otherwise, we remove the corresponding opening bracket. And at the end, we just check whether our stack is still empty or not. If it is empty, then that means our expression is balanced. Otherwise, it is unbalanced. In the main function, we take a string input and we just print true or false according to the answer value we get from our is balanced function. So this should work fine. So now let's give a expression. Now as we can see, this should return true, and yes, it does. So this is returning true. Now let's just do it for another expression, a bit complex this time. Now these two brackets are balanced, these two are balanced, then we have another set of balanced, and these are also balanced, but the final two closing brackets are unbalanced. So this expression should return to us false, and so it does. So our is balanced function is working perfectly, and we have perfectly coded the answer to this question. So this is basically how stacks work. The last element leaves first, and this is how we implement it in several problems. One practical use case of stack is whenever you use MS Word, when you type something, let's say you have to use backspace. So when you use backspace, the character that you had entered last is the character that you delete first using backspace. So that is nothing but a stack. So that is just one example of the use case of a stack. So if there are any doubts, just type them in the chat box. Otherwise, just type it is clear and I'll move on. So now we move on to the final topic of the day, that is queues. This is the second data structure that we are going to study. So like stacks, queue is also an abstract data type, but unlike a stack, a queue is open at both ends. That is, elements are inserted from one end and deletion takes place from the other end. In programming terms, the operation to add an item to the queue is called enqueue, whereas removing an item from the queue is known as dequeue. So these are the operations that we are going to perform in a queue. The enqueue function inserts an element, dequeue deletes an element, front returns the element in the beginning of the stack, getSize returns the present size of the stack, and isEmpty tells us whether our queue, I mentioned stack, sorry, getSize returns the amount of elements present in the queue, and isEmpty tells us whether our queue is empty or not. So one thing to note is that whenever we have to remove elements from a queue, we can only do it from the beginning of the queue. We cannot access the elements in the middle or at the end. We insert new elements at the end and we remove elements from the beginning. So that is how queues work. Now the implementation of a queue is a bit more complex than that of stack. We need to have two pointers, front and rear, which keep the track of the first and the last element in a queue. When initializing the queue, we set the value of the front to -1 and rear to 0. When we enqueue an element, that is, we insert an element into the queue, we increase the value of the rear index and place the new element in the position pointed to by the rear index. And when we dequeue, we return the value pointed to by the front pointer and then increase the front index to point to the second element, which becomes the new first. Now, before enqueuing, we check that our queue is already full or not, and before dequeuing, we check whether our queue has already become empty or not. When we enqueue the first element, since we had set the value of front to -1, we set the value of front to 0. And when we dequeue the last element, we again reset the values of front to -1 and rear to 0. So now let's check over the code for a queue. As like with stack, I have already designed it and I'll just take you through the code. So this is the queue code. We have the header file, and now coming to the class queue. Now we have an integer pointer data. Now the next index is basically the rear that was mentioned in the presentation. The first index is the front that was mentioned. The size of the queue stores the present size of the queue, that is the number of elements we have in the queue, and capacity is going to hold the total capacity that we are going to give to our queue. Now our queue will have the constructor will have a parameter s, which is going to denote the maximum capacity of the queue. We initialize an array, data is equal to new int s. We initialize our next index with 0, our first index with -1, and our size with 0, and capacity with s. So after the constructor is done, we go to the getSize function. Now we already have a variable which stores the size of the queue, so we directly return the size of queue variable. We have our isEmpty function. Now we have our size of queue variable, so we can just check whether the size is 0 or not. If it is 0, it's going to return true, otherwise it will return false. Now coming to the enqueue function. First, we check whether the size of our queue has reached the capacity or not. If our size queue has become equal to the capacity, this means that the queue has become full, so we print the message queue is full and we return. Otherwise, we have our next index through which we insert elements. So we write data of next index is equal to element, and then we update our element. Now, we cannot directly write next index plus plus like we used to do with stacks. That cannot be done with queues. This is because the insertion and deletion occur from different ends. Let's say we have a queue which can at most hold 5 values, and we insert 5 values 1, 2, 3, 4, 5. Now after that, let's say we remove 2 values from our queue. So we will end up removing 1 and 2 from our queue. Now the first 2 spots in our array will become empty, and our front will point to 3 and our rear will point to 5. Now our queue is not full, so we can insert new elements. But after inserting, if we just directly write rear plus plus, then our rear will end up going out of bounds. So to avoid that, we write rear, or in this case next index, is equal to next index plus 1 mod capacity. So in the example, we had taken our capacity to be 5. So once the queue is full, the value of our next index will be 4. Now if we remove an element, the first space in our array will become empty, and after that we have to insert the new element in that space. So we do next index plus 1 mod capacity. So the next index was 4, capacity was 5, so 4 plus 1 mod capacity gives us 0, which basically means it circulates back to the first index. And like we discussed, if we are going to insert the first element, then we have to make first index is equal to 0. It was previously minus 1. And after that, since we have inserted an element, we are going to increase the size of our size queue variable by 1. So this is the enqueue function. Then we have the top function, or basically the front function as mentioned in the presentation. We first check whether our queue is empty or not. If it is empty, we print queue is empty and then we return 0. Otherwise, we return the data of first index. Our first index pointing to the beginning of the queue. Now coming to the dequeue function, this is going to be the exact opposite of the enqueue function. We have we check whether our whether our queue is empty or not. If it is empty, we print queue is empty and we return. Otherwise, since our return type is integer, we need to return the value we are going to remove. So we store that value in our answer variable. Then we update first index in the same manner that we had updated next index in the enqueue function. This is basically to take care of the case that when the first index reaches the last value in our array, it needs to circulate back to the beginning again. And that is why we use this code first index is equal to first index plus 1 mod capacity. And now since we have removed an element, we decrease the size of queue by 1. We write size of queue minus minus. And if our queue has become empty, we initialize our first index and next index values to their original ones. That is, we make first index is equal to minus 1 and next index is equal to 0. And then we return the answer, that is the first element that we had stored in the answer variable, we return that. So that brings us to the end of our queue function. Let's just go through them again. We have the constructor, which has the maximum size of the queue as parameter. We have the getSize function, which returns the size of the queue. The isEmpty function tells us whether our queue is empty or not. enqueue pushes an element into the queue, and top basically brings us the frontmost element in our queue. dequeue removes an element from the queue. Now I have prepared a small code to test this queue. So we declare queue of 5. So this is going to at most hold 5 integer values, and then we push in values. We push 10, we push 20, 30, 40, 50. Now once we have enqueued 50, our queue has become full. So when we try to push in 60, it should display the message queue full. Then we print the topmost element, that is the frontmost element, so it should return 10, and then we dequeue 3 times. So the first 3 elements should be removed from the queue and they should simultaneously be printed as well, since dequeue had the return type int. So it should print 10, 20, 30. Now we have 40 and 50 remaining in our queue. So when we write get size, it should return to us 2. And since our queue is not empty, so is empty should return false, which basically means it should print 0, 0 denoting false. So let's try to execute it and check. And this is the output, and we check queue full 10, 10, 10, 20, 30, 10, 20, 30, 2, 2 and 0. So our output has matched. So this means that our queue is functioning exactly as it should have. So that brings us to the end of the implementation of the creation of the queue class. So now let's test our knowledge. So before that, as in the case of stack, C++ also provides an inbuilt queue, and it's in the standard template library. For this case, we use the header file #include queue, and the syntax is similar to that of stack: queue, data type, variable name. For example, queue int q1. So we create a queue of type integer. And as in the case with stack, the inbuilt queue in C++ does not have any end limit. It can keep on forever adding values to it. So the functions that this queue is going to provide to us is the push. Push function is basically the enqueue function. It inserts a value into the queue. Then there is the pop function. The pop function deletes the element from the queue, that is the dequeue function. The front function returns the element at the front of the queue. The size function returns the number of elements present, and the empty function returns true if the queue is empty, else it returns false. So now we use the knowledge we have gained about queues practically in the code. So the question is that we have been given a queue that can store integers as the data. Now we need to write a function that reverses this queue itself. We don't just need to print the queue, we have to reverse the queue itself actually. So for example, let's take our size of queue to be 6. Then we enter 6 integers, and here 1 is at the front of the queue, 10 is at the rear. And now the sample output should be the integers printed in reverse order, and not only just printed, the change should be reflected in the queue as well. 10 should be at the beginning and 1 should be at the end. So now let's implement this. So I have already written the main function, that is we declare a queue, we have the int size, we enter the size and then we push in values, and then we call the function reverse queue. So here actually in this question we are also going to use recursion as well as the queue data structure. We are also going to use recursion. So since we are going to use recursion, how are we going to design it? We are going to have a queue. We design a base case where the recursive calls will stop. After that, we separate the first element from the queue out. We reverse the remaining queue using recursion, and then the first element that we had separated out, we insert it again at the end of the queue. So let's code it. So first the base case. Now since we are going to separate the first element at each recursive call, at one point there are going to be no elements left in the queue. So our base case should be when the size of our queue is 0. If so, we directly return without doing anything. Otherwise, we take a temporary variable, and to this we store the frontmost integer of our queue. After this, we remove this integer from our queue. Sorry, there's a spelling error. and then we recursively call our function reverse queue on the remaining queue. And now, as in the case we have seen earlier, once we do the recursive call, we have to assume that this is going to reverse the remaining queue. And we assume that the remaining queue has been reversed. After this, we just add our first element which we had separated out into the queue again. We just push it into the end of the queue. And then we return. So once, let's go through this. We have input dot size is equal to 0. That's our base case. When our queue becomes empty, we return. Otherwise, we remove the first element from our queue, we pop it from the queue, we reverse the remaining queue, then we push the first element again at the end of the queue. And at the end of all the recursive calls, our queue should be reversed. So now let's try to code it. We have coded it, so let's try to execute it. So let's take the example that we had given. I'm going to provide 6 integers to my queue, and they are 1, 2, 3, 4, 5, and 10. Now, yes, so we see that the queue has been totally reversed. We now print 10, 5, 4, 3, 2, 1 because in the main function we had first entered the values in the queue and then just directly printed all the values in the queue. And we had entered in this fashion, but it's being printed in the opposite fashion. So that means that our queue has been totally reversed. So with that, we come to the end of our webinar today. We have discussed recursion, stacks, and queues, and I hope that I have been able to at least help you gain a brief understanding of what these topics mean. So yeah, thank you. If there are any doubts, you can type them in the chat box. If not, well, yes, the session is over. And if so, yeah, thank you. See you soon. Bye bye.